Hello, everybody. I thought I would make you a little video for the 7 organic reactions. Just want to check one thing. Okay, that seems to be okay. Well, if you see on the screen, maybe you see me down here, hello. Um, in a different order than when I presented them in class, I wanted to represent these to you. Just jump right into it. Notice here we have the first reaction. You know this from living environment. This is called glucose. I'll write that there, glucose. Recall when glucose reacts with, in the presence of an enzyme reacts, decomposes here, it produces an alcohol, not just any alcohol, ethanol, a 2-carbon alcohol, and also carbon dioxide. What is this called? Well, this is called fermentation, which of course is spelled fermentation. Remember, on part 2 questions, you won't have a word bank, so you'll have to make certain you commit these 7 reactions, their names, to memory, at least their names. Next, in a slightly different form, I've presented the second reaction here. Notice I have an organic substance reacting with oxygen, and in the presence of oxygen produces carbon dioxide and water. As we know, that is called combustion, which is just a highfalutin term for burning. Reaction number 3. Well, we have a series of, notice, hydrocarbons. They're each double bonded, so I hope you guys know that these are what we call unsaturated, almost tripped on my own words, be careful, unsaturated hydrocarbons. Now, I'm adding one to another, to another, to another, and if you notice, I have these things called ellipses. Ellipsis means there are a lot of other molecules in front, a lot of other molecules behind. Remember, maybe there are tens of thousands of them, and we add them end to end to end to end to end to end, and so on, ad nauseum. We break all those double bonds, we have single bonds, and we make an incredibly long chain, maybe 10,000, 20,000, 50,000 units long, called, that's right, a polymer, in a process that we altogether call polymerization. Recall that each unit of a polymer is called a monomer, an identical subunit that repeats many, many hundreds, thousands, tens of thousands of times. The fourth one we're dealing with today, this is the easiest because I didn't really go into what all a fat was, and I didn't really spend too much time on what a soap was. If you just know that a fat plus a base, a strong base, like sodium hydroxide, makes soap and a 3-carbon alcohol with 3 OH groups on it called glycerol, well, we know that any process that primarily makes soap is called saponification. No, it's almost kind of in the name. Sapos can be rearranged to form soap. Yes. And next. Reactions 5 and 6 are kind of sister or brother reactions, if you will. Notice I have a hydrocarbon reacting with something from group 17 to make what we call a halocarbon or a halide. You'll find the form of this on table R. Now notice in this case I have a double bonded and unsaturated hydrocarbon, an alkene, or it could also be an alkyne, but it's almost always an alkene, reacting with I2. And look what happens. The I2, I, and an I, came in, they broke the double bond here, leaving you with a single bond. One I went on this carbon, and the other I went on that carbon, to make something called a diiodo, just to give you the full name, diiodo, specifically 1,2-diiodo propane. If you notice that whenever you have this reaction, which of course we call addition, you are breaking the double bond and you are adding an I and an I to either side of the broken double bond. Now, of course, if this were an F2, you'd be adding an F and an F. If this were BR2, you'd be adding a BR and a BR. Remember my little example of this in class, my little analogy was that imagine you have a school and suddenly you have this extra money, this extra bond. Well, you're able to hire 2 new teachers. And I said it's a package deal from, I don't know, Sawanica. And they come and they're added to the school. You didn't lose any, you didn't change any number of H's here. They stayed the same. You just merely added 2 new teachers, an I and an I, taking the place on either side of that broken double bond. Now, to stick with the school analogy, here's a school. This is something that happens quite commonly. Of course, not to Mr. Segelke, who hasn't been absent very much. He hasn't needed, that's right, he hasn't needed the phenomenon of substitution. Now in substitution, notice, unlike in addition, let's go back up here, addition, you have an unsaturated hydrocarbon. You have a double bond or maybe a triple bond, which you can break and add to either side. We don't have that here. In substitution, there is no place to add anything else to these carbons. Why? They all are doing the happy carbon dance. Each one has 4 bonds, or I should put it this way, are connected to 4 other atoms. Therefore, we have to substitute. So let's say, for example, here's one teacher here who's feeling sickly today. So that teacher takes the day off and is replaced by one of the I's here. And notice here, so instead, what changed here is that H has now become an I, and now that H is off away from the school building, and he's hanging out with the other I. Remember, we have II here. One of the I's came in, one of the I's stayed behind, and then that I bonds with the H that has been substituted. So again, here we have a saturated hydrocarbon and alkane. Remember, I did that, or I said what I used to do. Saturation substitution and single bonds. It's SSS, saturation substitution, single bonds. That will lead you always to choosing the correct one. Okay, and we have one final reaction. The spiciest of them all, I think, it's called esterification. Now, how do I know? What is it? First, you need to know what an ester is. Well, remember, the ester has this complicated functional group in the middle of the molecule, thereabouts in the middle. You have a C double bonded to an O, single bonded to an O, and remember that O is also bonded to one or more carbons on the other side. So once you identify this as an ester, you know that the only process that can make an ester is called esterification. Where did it come from, class? Well, we have what I call the far side. I like to call it Malvern. Things happen there, nothing much interesting, so we call it the far side. Now notice that that far side, 3 carbons, has the same number of carbons that came from the alcohol. In the reaction that forms an ester, an alcohol, remember ending with the OH, reacts with an organic acid, which we identify with the C double bonded OOH. And notice that the 5 carbons in the organic acid are on the O side, which I like to say, of the molecule. The O side, of course, is headed by the carbon that touches both O's. It's like where everything is happening in the molecule. Now, of course, if we wanted to name this particular molecule, we would do the following. We notice that the far side has 3 carbons, so which we call propyl. A propyl is a 3-carbon chain. The other side, the O side, is going to end in O8. And I have 1, 2, 3, 4, 5 carbons. That's pentane, which becomes pentanoate, which is written, again, altogether, propylpentanoate. So again, you have an alcohol, which reacts with an organic acid to make an ester and water. Well, Mr. Segelke, where does the water come from? Well, remember the OH from the alcohol, which is nice and dark here, and the acidic H from the acid come together and they form water. The rest of it come together to form the ester. Well, I hope this was helpful because I notice over the years that students have the most trouble with this. And again, I just have to suggest you sit down and you spend a little time memorizing. Like this would be a great case of saying over to yourself a couple of times that an alcohol plus an organic acid gives you an ester plus water. It'll clarify a little memorization. Well, I hope you enjoyed this. I certainly enjoyed making it for you, and I'll see you tomorrow.